In this video, I want to give you an intuitive explanation for why time appears to slow down for moving objects in special relativity. So Einstein tells us that if I were to somehow watch someone in let's say, a spaceship moving close to the speed of light or extremely fast, then it would seem to me, watching them, that time moved in slow motion. So clocks would run slower. Every process, from throwing a ball to jumping up and down, time itself seems to move slower. And there's an intuitive way to see this result, and we can do it in 3 steps. So I'm going to start by trying to argue why it makes sense for us to say that the speed of light is constant. And then I'm going to argue that if I were to hold up a ruler vertically and move about, then I'm going to agree on the length of that ruler with someone who's standing still. And that might seem a little bit crazy. I mean, why do I have to show that? But it turns out that in special relativity, that's not the case in the direction of motion. And then finally, the final ingredient is going to be to give an argument showing why we need time to slow down if the speed of light is constant, and by what factor. So let's get started. So the first step is going to be trying to understand why Einstein needed, or why we all needed, the speed of light to be constant in the first place. Not with Einstein, but with the principle of relativity from Galileo back in the 1630s. And what this principle says is that the laws of physics are the same regardless of what velocity you're going at. Let's say here's Galileo, and he's watching someone on a boat or a ship, and he throws up his apple and it comes straight back down according to the laws of gravity. But as he watches the man on the boat who throws up his apple, he sees that it instead forms a kind of arc. And so he might think, well, okay, well, that man is moving at some velocity. But then he thought, well, what about from the perspective of the man on the boat? From the perspective of the man on the boat, he throws up his apple and it goes up and down according to the laws of gravity. And instead he sees Galileo move in the opposite direction, and his apple appears to go in an arc. And so Galileo is a smart man, and he thinks about this, and he comes up with, and he argues that this is telling us, he argues that in fact there is no experiment that we could have done to say who is moving and who isn't. Instead, there is no absolute velocity, there is only relative velocity. I'm only going 10 meters per second relative to something else. And there's no experiment I can do to tell me who is moving and who is stationary. And so this is the principle of relativity. And so that's all well and good for about 200 years. But very curious happens. So this fellow here, that's James Clerk Maxwell, and he discovers that or he puts together some new laws of physics, and he notices that there is a speed built into the laws of physics. He finds that the speed of light is kind of baked into the equations that govern the world. And so this is very curious. And why is this a problem? So, because let's say I'm on my boat and I see some light go past. Well, now I can measure the speed of that light, and according to the thinking of the time, this light is going through something, it's propagating through something, which we'll call the ether. And so, a speed wouldn't make sense if it's not relative to anything. And so it must be relative to whatever it is that this light is propagating through. But now, if I'm moving and I see that the light is traveling at a different speed, I can say, oh, well, that means that I'm in motion relative to the ether. And so now there is an absolute velocity. And so this idea of this principle of relativity has been thrown in the bin. And so physicists and experimentalists went out to test this. They went out to find this effect, to see that when I'm moving, I'll measure a different, moving relative to this ether, I'm going to measure a different speed of light to when I'm not. And I'm going to have some kind of notion of what my absolute velocity is. And so that's Michelson and Morley. And what's a lot like a boat traveling through space and time? Well, the Earth. And so they do some very impressive, precise experiments, and they find no effect. No matter how they do their measurements, they can find no difference in the speed of light. It doesn't seem to matter how we're traveling relative to this ether. The speed of light is always exactly as it appears in Maxwell's equations. It always has the same value. And so the experimentalists are quite confused. And so it takes another 15 years, around 15, until Einstein appears in 1905 and says to all of these people, actually, you're all correct. The experimentalists, your experiments were perfect. There wasn't anything wrong with them. There isn't anything wrong with the laws that Maxwell has compiled. And even Galileo is right. The principle of relativity is correct. And so he says, well, in order for all of you to be right, it must just be that the way the world works is that the speed of light is constant. It doesn't matter how fast you're moving, you'll always see the same speed for light. And so we can take this angry Galileo out of the trash bin. And I just want to emphasize how bizarre this truly is. What Einstein is proposing is that if I, watch some light go by, so I'm in my boat and I watch some light go by and there it goes. Now I turn on the turbo and I fly ahead. And yet the light continues to move at the same speed. I can't catch up to it. No matter how fast I go, it still seems to just have the same velocity. It's like I can never catch it. That's absolutely bizarre. And yet, so you might think, okay, well, this is just some ridiculous theory, and clearly there must be some other explanation. And yet this is exactly why we can liberate so much energy from mass. Like the reason that an atomic bomb contains so much energy follows from this line of thinking, from special relativity, and many other effects. And so it does seem that this is just the way the universe is. The speed of light is constant, and you can never catch up to it. So that's our first ingredient. The speed of light is constant. And this is just something extra that from experiments and from observations of our world, that just seems to be the way that the universe is constructed. So now we're really getting closer to time dilation. So what does it mean for the speed of light to be constant? Well, speed is the amount of distance that is traveled in a given time. And so if the speed is always going to be the same, then we better be able to mess with distances or with time. And so it turns out in special relativity, we do both. But in order to isolate what the effect is on time, in order for us to have this intuitive understanding of how time must change, we're going to look for a situation where distance is it would be impossible for the distances to change. And so a scenario that fits this bill is orthogonal distances. So if I have a ruler on my ship, here's my ruler, and I'm moving in a direction orthogonal to the ruler, then we're going to argue that it's impossible for the length of that ruler to change in different frames. So here's this little character, and he's curious about why. So let's just put down this clear rule. So in special relativity, sometimes it can seem like some of our basic intuitions about the world are violated. For example, things can happen at different times from different frames of reference. But it's essential that even if things can happen in different spatial locations or at different times from different frames of reference, from when you're moving at different velocities, it's essential that in special relativity the same events happen. We agree, if a star explodes, we agree whether we're moving at 100,000 meters per second relative to the event or whether we're standing on a planet right next to it. Everyone in the universe will agree that a certain event happened at some point and in some time, but not necessarily agree that it was at the same point and the same time. What can't happen is that the star survives for one person but dies for another. There are no parallel universes in special relativity. And what I mean by that is, for example, let's say a comet were to hit the Earth. There can't be a frame where the comet completely misses the Earth and another frame where it hits it, because otherwise there'd be two different universes, one where life on Earth is extinguished and another where it isn't. So why do I bring all of that up? Well, I'm going to use this simple thought experiment to give an intuitive reason why orthogonal distances can't be changing in special relativity. So let's assume that we've got our circle of dough and we've got our cookie cutter. And our cookie cutter is going to fly through at relativistic speeds and cut us a little cookie from the cookie dough. So here's a side-on view. And so now we're watching from the frame of the cookie dough. And so the cookie cutter is flying towards the dough. And that means that if we have some kind of contraction, and so we can do a very similar argument if instead the effect was expansion, so let's just go with contraction, then we'd make a very reasonable sized cookie and we put 5 little chocolate chips on it, and possibly we make another cookie. However, let's consider the same situation from the point of view of the cookie cutter. Now, for the cookie cutter, the dough is flying towards it at high speed, and so the same effect must happen to the dough. And so, indeed, the dough contracts. But now, our cookie cutter, it might even completely pass around the dough and not interact with any of it. And so we end up using all of our dough for a single cookie and putting thousands of little chocolate chips on it. And so clearly we've now split into 2 parallel universes. And so this kind of thought experiment can show us that orthogonal contraction or expansion should not be allowed in relativity. And so we're fine for using that ruler that guy had in that ship. All right, now we're finally ready we've got the two previous ingredients, speed of light is constant, orthogonal distances don't change, and now we can show that time dilation happens in special relativity, and even figure out by what factor. So here's our genius contraption. We've got a man on a ship, and he has a little light clock. So all that's going to happen is a little bit of light is going to be emitted up here, and then it's going to bounce between two mirrors. And we're going to say that it goes from one mirror to the other in one time unit. And so for the man on the ship, he watches the light go like this. So it goes tick, 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 tick. But what about us standing outside the ship and watching him move? So we see the ship go that direction. And so for us, we see the light go tick, 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 tick. So tick, 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 and onwards. But there's something odd here, because for the man on the ship, the light is only traveling this distance. But for us watching, the light appears to travel this distance. So if you know your right-angled triangles, this distance is longer than this distance. And so if we were to agree about time, then we'd get into a situation where for us, the light has traveled a longer distance than for the man on the ship. And so we would disagree about the speed of light. Now, as I just said, in order for the speed of light to be constant, we have to be able to mess with distances and times. And so in this case, since distances have been taken off of the table by the previous discussion, the only thing we're going to mess with, the only thing we can mess with in order for us to agree about the speed of light is time. And so we're going to figure out that we have to see time as moving slower for the man on the ship. Because this schematic, in a unit time, we can't agree that the light has reached the other mirror. We can only say that it's got a distance c towards that mirror. And so for us, in a unit, it takes a little bit longer than a unit time for the light to hit that mirror, which for us is further away than for the man on the ship. And so he'll see his clock go tick, 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 but we'll see his clock go tick, 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 tick. So first of all, let's just note that we've just concluded, or we've just seen logically, that in order for the speed of light to be constant for both of us, time has to be slower for the moving frame from our perspective. But we can go further than that, and we can figure out exactly by how much. So we've already seen the logical reason for time dilation in special relativity, which is great. But now let's figure out by exactly what factor time should be slower from our perspective. And we can do this using the right-angled triangle. So in unit time, we know that this guy who's moving at a velocity v, let's say, has moved a distance v. So he moved, his velocity is v distance units in one time unit. And we also know that because the speed of light is constant, for us, we see the light moves a distance c in one time unit. And so now we get a little bit of help from our friend Pythagoras, who said that the length of the hypotenuse squared is equal to the lengths of the two sides squared, the sum of the squares of the two sides. And we can see that the vertical distance that we say the light has moved is equal to the square root of c squared minus v squared. So what does the man on the ship say? Well, he says in unit time, it's moved a vertical distance c. And so the ratio of these two distances is going to tell us the ratio that we need to slow down time in order for us to agree. So in order for us to see the correct speed of light, the only speed of light, we have to slow down time for this moving object by this factor. And so we can do a little bit of algebra. So we bring the c inside the square root, and we see that this is 1 minus v squared over c squared, square rooted. And this is actually a super common factor. So this is the factor that we need to slow time down for the moving object. And it's given by this Lorentz coefficient. So it's actually 1 over the Lorentz coefficient, and this turns up absolutely everywhere in special relativity. And so there's our final piece of the puzzle. We've shown that time slows down for moving objects when viewed from a different frame, and we've even shown by how much. 1 over this Lorentz factor, which is equal to the square root of 1 minus the velocity of the thing moving squared divided by c squared. And all we needed to get there was, assuming that the speed of light was constant, knowing that orthogonal distances don't change, so that we were only messing around with time, and finally just a little bit of help from Pythagoras. So there we go. So where do you go next to continue the path of special relativity? Because we've only just scratched the surface. So far we've only seen time dilation. But in fact, as I alluded to, in the direction of travel, so if this thing is moving in this direction, you have length contraction. So distances do change in the direction of motion. And then there's this whole issue of simultaneity. So I mentioned that in special relativity, we can have a disagreement about where or when something happened, but not if it happened. But that's actually quite crazy. We can disagree about when something happened, and that can lead to, for example, this paradox, which, unlike our cookie paradox, which really can't happen in reality, this isn't a paradox. This is possible in our reality. So there's this barn, and a guy is running into it with a fence. This is a screenshot from a video. I'll put a link in the description. But in one frame, the doors to the barn can both be shut at the same time, completely enclosing this ladder. But in another frame of reference, the barn is too small to contain the ladder even. And so it's impossible for both of the barn doors to have been shut at the same time. And so this really comes from this issue of simultaneity not being preserved by special relativity. And you might say, well, is this all just an illusion? Is this all just a case of seeing things differently when you're traveling at different velocities and it doesn't really affect anything? Well, that's not the case. If I send something very fast away from me and then bring it back, it turns out that doesn't undo like the change in velocity and coming back. That doesn't undo the effects of special relativity. It still experiences time dilation, meaning that if I were to send, let's say that I had a brother and he was born at the same time as me, and I sent him away on a trip to our nearest star extremely quickly, then he might have aged, I might age, let's say, 10 years, and he might only have aged 2 years. And so you can get into these and so this time dilation can really come back and be in the same frame as you and really have consequences. And then, of course, beyond that, there's this whole equivalence between mass and energy, which follows from this line of thinking, and that's applying similar arguments to the ones we just discussed, but to momentum. And beyond that, you can get to topics like magnetism and beyond. So I'll put some links in the description, and I hope that this helped somebody.